Hello and welcome to Bedroom Physics. Today I'm going to be talking about Newton's laws of motion. Before we jump into Newton's laws of motion, we need to know the names of a couple interactions. So the first interaction that we need to know is something called contact force, and contact force happens when one body directly interacts with another body. Say if you push a book, or if you pull a book directly, then that'll be a contact force. The normal force is a force that if a body is sitting on a surface, then the force the surface exerts on that body is called the normal force, and also this force is perpendicular to the surface. The next force is called the friction force. So if there's a body moving on a surface, then the friction force will be parallel to the motion and opposite in the direction. The next force is the tension force, and the tension force is the force that a fully stretched out rope exerts on a body. And lastly, we have weight, which is the force that gravity exerts on the body. We also need to know what the superposition of forces are. And if you remember back from vector addition, we can add up a bunch of different vectors together and we can get one vector. Force is actually a vector as well. So if we add up all the different forces, then we're going to get a force net, or the overall force, which can be represented by a single vector rather than all of these different vectors. Of course, these are all the forces being exerted on one body, and then they can be represented by one vector. This addition of all the forces is known as the sum of the forces, and it's noted by this little E-looking sign. Okay, so now that we know that, we can start talking about Newton's laws of motion. So Newton's first law of motion is a body acted on by no net force has a constant velocity, which can be zero, and zero acceleration. So if I had a ball, and this ball was moving or resting in a vacuum, if the net force on the ball was zero, then the ball would continue to move or stay at rest indefinitely. And so long as the net force on the ball stays at zero, the body will either stay at rest or stay in constant motion, or to be specific, constant velocity. Now this tendency for a body to stay at rest or stay in motion is known as inertia, and it's at the very core of Newton's laws of motion. An important concept from this is the inertial frame of reference. So say you were in a plane and both you and the plane were in free fall. Now this is not going to be a perfect example because of the acceleration of gravity, but technically your motion relative to the earth is zero in the x and y direction. Now the frame of reference of this plane or the shuttle itself is not an inertial frame of reference because it has an acceleration. But u to the earth is we're using it as an example of inertial frame of reference. But anyway, you are not moving in respect to the earth. But let's say that the shuttle accelerates forward. Well, so long as you're not touching any of the edges or anything like that, and again, we are in free fall, the plane will accelerate and move forward, but you will stay in the same place. Relative to the plane, it'll seem like you are moving to the back of the plane, but actually you haven't moved at all relative to the earth. And of course, if the plane or shuttle started moving backwards, then it will seem like you're moving to the front of the plane or the shuttle. Now this also works for motion in a circle. So if you're in one position inside the shuttle and then the shuttle turns, you're going to stay in the same point, but relative to the shuttle, it'll seem like you've moved to the other side because it is turning. Newton's second law of motion is if a net external force acts on the body accelerates. The direction of acceleration is the same as the direction of the net force. The mass of the body times the acceleration vector of the body equals the net force vector. This is essentially just saying that the force is equal to mass times acceleration. Or if you want to do the sum of the forces, it'll be equal to the mass times the sum of all the acceleration vectors. For example, if there's a box, let's say box 1, and I exert a force on it, then I will give it a certain acceleration which is proportional to the force. If I exert a force on box 2, the same force, then I'm going to give that box an acceleration proportional to the force. And then we'll see that the mass of the first box times the acceleration that I gave the first box is equal to F, the same way that the mass of the second box times the acceleration that the force gives the second box is also F. And so m1 times a1 is equal to m2 times a2. Even though the accelerations and masses are going to be different, as long as the force is the same, this will remain true. Now I also wanted to talk about the units this entails. So a force, mass times acceleration, we're going to have kilograms times meters over seconds squared, and it's going to be a Newton, or N for short. So 2 kilograms times 5 meters per second squared is equal to 10 newtons. The last law of motion, Newton's third law of motion, is if body A exerts a force on body B, an action, then body B exerts a force on body A, a reaction. These forces have the same magnitude but are opposite in direction. These two forces act on different bodies. Essentially, what this is saying is that the force body 1 exerts on body 2 is equal to the force that body 2 exerts in body 1, but it'll be negative, meaning it'll be in the opposite direction. Pretty much what it's saying, if I push on this chalkboard pushes back at me with exactly the same amount of force that I pushed it. The only reason that in this case, the chalkboard didn't move, but say I pushed, I have a little end table here. I can push and pull the end table because my friction is greater than the friction of the end table, allowing me to move the end table even though it's exerting the same amount of force that I am exerting on it. Let's take you for example. Let's say you were pulling on a rope which was attached to a box. If we look at one end, let's say you and the rope. You are exerting a force on the rope, and as a reaction, the rope is exerting a force on you. This is an action-reaction pair. These forces are equal in magnitude, but opposite in direction. On the other end, we have the box, which exerts a force on the rope, and as a reaction, the rope exerts a force on the box. This is an action-reaction pair. These will be equal in magnitude, but opposite in direction. But not all pairs are action-reaction. If we look at the system as a whole, and then if we look at the force that you exert on the rope, and the force that the box exerts on the rope, this is not an action-reaction pair because there are two bodies exerting force on only one body. The forces are being exerted on the same body. And so Newton's third law does not apply because they have to be different bodies. Now, there is a special case when the rope is in equilibrium, meaning it has no acceleration, then these will equal in magnitude and be opposite in direction. The other case would be if the rope has no mass, or obviously the rope has a mass, but if we're doing a problem which treats the rope as massless, then they will equal each other in the magnitude but be opposite in direction. Now the last thing that I want to talk about is free body diagrams. I'll do some more of these in the example video, but I just want to go over the concept. So say we had a system and we have box B, we had a rope connecting box B to box A, and there's a force being exerted on box A. If we isolate box A has a force upwards being exerted on it. It has the force from the rope that's being exerted on it, which is a force downwards, and the force of gravity, which is also downwards. If we isolate box B, we'll see that the rope is exerting a force on box B upwards, and gravity exerting a force on box B downwards. If we look at the rope, we'll see that box A is exerting a force on the rope, and box B is exerting a force on the rope, and lastly, the force of gravity is exerting a force on the rope. So pretty much a free body diagram is just breaking down all the different forces reacting everywhere. Of course, you don't have to break them up. You can do everything here, but it will probably get kind of messy. This makes it way easier to do all of your Newtonian mechanics problems. Before I end, I want to say that These definitions are all from Sears and Zemansky's University Physics with Modern Physics, the 14th edition by Young and Friedman. Go buy the book. It's an excellent book. In fact, I'll probably put a link to it, Amazon link to it, in the description. In any case, this has been Newton's Laws of Motion. I hope to see you in the example video.